Hello, everyone. I'm Billy Younger, and I'll be teaching you a second lesson in trigonometry. Today, we're going to define the radian, which I've sort of alluded to in the previous video. I'm still going on the assumption that you all are at least somewhat familiar with degrees. You know, there's 360 degrees in a circle and that sort of thing. But we're going to use the idea of circumference, which would be perimeter if it was any shape other than a circle, but it's basically the distance around the circle. And we're going to use that common formula that I suspect you've all heard before. In terms of the radius, it's the circumference equals 2 pi times r. And I'm going to use that to help you understand where the idea of the radian measure came from. And then I'm going to walk you through creating a unit circle and maybe even get you started a little bit on figuring out two special triangles to help us figure out the special angles of the trig functions, and then two, start to fill out the actual coordinates on the unit circle as opposed to just the special angles. So let's turn it over to my document cam and get you started. Now I've drawn circles here and some other lines in preparation for what we're doing. They're drawn, most of the stuff's drawn in pencil, so they're not that easy to see. The main thing is I'm just marking them so that you can see them to some extent. First off, we're going to start with the formula circumference is equal to 2 pi r. Well, it was originally noticed that the distance around a circle was directly related to r. Normally in mathematics, we write that as c proportional to r, and then it's just a matter of figuring out what constant would go there to make this into an equation. Well, later experiments, trial and error and stuff of that sort showed us that there was a consistent ratio between the two, so that c over r in fact turned out to be about 6.28 at first, which we now called 2 pi. Okay, pi being 3.14159. So that is the actual ratio. It turns out this number is in fact a non-terminating, non-repeating decimal. It's what we call an irrational number. It cannot be made as a ratio of two whole numbers. So that irrational number 2 pi, just like the pi itself, is irrational. So now we're going to use this idea to understand where the radian comes from. So it turns out that if you double this radius, you double the circumference around, you triple the radius, you triple the circumference around. That's why we found that c is proportional to r. But also, if you cut the circle in half, then it's just half the circumference. So in fact, the distance around would be pi r. Or if you cut a quarter of it out, the distance around would be 3 pi over 2 r. And then if you did a quarter of the circle, of course, it would just be pi over 2 r, because 2 pi over 4 is equal to pi over 2. So a guy by the name of Roger Coates in 1714 was the first person to actually, in writing, identify this. And he didn't actually give it the name radians, but basically he did everything else that we know about it. So we give him credit for creating the radian system. So it turns out it's actually part of a more general formula, which says that if you let this radial line, the line that goes from the center of the circle to the edge, that is in fact a radial line. Anything that goes radially inward or outward is radial. If you allow that to sweep out an angle theta, which I'll indicate by this, actually gives us an arc length, and that arc length we'll call S. So it makes this arc length right here S, and the general formula for it is S is equal to R times theta. But in order for this formula to work, you have to identify theta in radians. Now, as you can see, since the radians came from a ratio of circumference to radius, and obviously you measure this, say, in centimeters and this in centimeters as well, and a centimeter divided by a centimeter is basically a unitless number. So the radian actually isn't a unit at all. So you might choose to put the word radian on the end just to keep things clear, but you don't actually have to. It's purely a pure number. So we're going to stick with that angle, and I think we're going to stick with that notation. And you can see angle of 0, of course, would be 0 degrees or 0 radians. But if you go half a circle, that would be 180 degrees, which we're going to call pi radians, because if you went a whole circle, it would be 360 degrees, which is 2 pi radians. So automatically we have a nice little conversion factor. We can see that 2 pi radians is equal to 360 degrees, or dividing both sides by 2, we could say 2 pi radians is equal to 180 degrees. Again, you don't really have to write that radian out, but sometimes it's better to. Now, as you know, you can make a conversion factor out of any two things that are equal. All you have to do is put one on the numerator and one in the denominator. So there's two conversion factors that come out of this. You can say pi radians over 180 degrees, or you can say 180 degrees over pi radians. Those are your conversion factors. So if you happen to have degrees, you'd want to multiply by this first one, because if you have degrees, then it's not in a fraction. So it's technically in the numerator of a fraction if you were to make one. And that degree would cancel out with a degree down here, and you'd be left with radians. So you want to multiply it by pi over 180 if you have degrees. If you have radians, again, the radian would be in the numerator because there's no fraction. That radian would cancel out with this radian down here, which really neither one's a real unit. So you'd actually have to multiply by 180 over pi to convert radians to degrees. So now we know how to convert them. And now I'm going to work on creating the unit circle now that we have some sense of what this radian measure is. It's really good practice, and I suggest you try it. Try computing what radian measure is on the face of a clock and going, say, from midnight to 1 p.m. or 1 a.m. or midnight to 2 p.m. or 2 a.m. if it's noon, and you know what radian measure measures a 1 minute arc. So stuff like that. That would be 1 minute on the face of a clock. That is not 1 minute of arc. That's a different thing. All right, so let's start off with our circle. So I've drawn here a circle whose radius is supposed to be 1. Obviously, it's not 1. I just made it big enough so you guys could see it. And what I did was I made an x-axis and a y-axis, and this is the negative x-axis, and this is the negative y-axis down here. And what I'm going to do is fill out the radians and the degrees. This is 0 radians, and it's also 0 degrees. But if you go all the way around, I know you lost me there because I'm not showing the whole circle, but if you go all the way around, you know that's also right back where we started from. So that's 2 pi radians, but it's also 360 degrees. So this line right here indicates both 0 degrees, 0 radians, and 2 pi radians and 360 degrees. Now, if you go halfway, we know that would make this into pi radians. And if you go all the way, that would make this into 3 pi over 2 radians. Obviously, of course, the pi radians is 180 degrees, and the 2 pi radians is 3 pi over 2 radians is 270 degrees. Similarly, if you only went halfway to pi, this would be pi over 2, but that's also 90 degrees. So now we have all our angles, our basically 90-degree increment angles. Now I'm going to do all the other special angles. If you'll notice, these darker lines that I've drawn, I've left the center ones intentionally a little bit lighter. These darker lines that I wrote, they're going to be, notice you can slice up this pi angle, this angle from 0 to pi, into 1 slice, 2 slices, 3 slices, 4 slices, 5 slices, 6 slices. So you can automatically see that each of these is 1/6 of pi. So you now have that this is pi over 6. This is 1 pi over 6, 2 pi over 6. Well, 2 pi over 6 is the same thing as pi over 3. Just converting fractions or reducing the fractions is pi over 3. This is 3 pi over 6, which is pi over 2. So we got that, and that agrees with what we're talking about. So then this would be 4 pi over 6, but of course 4 pi over 6 is just 2 pi over 3, again, reducing fractions. And then we have 5 pi over 6, which is just going to be 5 pi over 6. No reduction to be had there. 6 pi over 6, which is just pi, and that confirms what we already had. 7 pi over 6, there's no reduction in that one, so I'm just going to write 7 pi over 6. This would be 8 pi over 6. Of course, you can reduce 8 pi over 6 to 4 pi over 3. 9 pi over 6, of course, reduces to 3 pi over 2, confirming that measurement. 10 pi over 6, of course, reduces to 5 pi over 3. And then 11 pi over 6, there's no reduction to be had there, so that's just 11 pi over 6. Notice I'm trying to do a little tilde shape there on the pi. That's really a better way of writing pi, but sometimes it just reduces to a straight line and two other straight lines. All right, and then finally 12 pi over 6 is 12 divided by 6 is 2, so that's just 2 pi, so we confirm that. Now, you might also notice the lighter line cuts 0 to pi into 1 slice, 2 slices, 3 slices, 4 slices. So clearly that angle is going to be pi over 4. So I'll write pi over 4, 2 pi over 4, which again is pi over 2, 3 pi over 4, 4 pi over 4, which again gives me pi, 5 pi over 4, which cannot be reduced, 6 pi over 4, which reduces to 3 pi over 2, and then finally 7 pi over 4. So now we have all the special angles. So why are these the special angles? Well, these are the special angles because we've decided that those are ones that are worthwhile knowing, and they come rather easily from two special triangles, two special right triangles, and I'm going to show you those now. So this one's actually called the 30, 60, 90 triangle. 30 degrees, which is pi over 6, 60 degrees, which is pi over 3, and 90 degrees, which is marked by that, which also you can tell is pi over 4, or excuse me, pi over 2, of course. So when you draw this triangle, the pi over 3 is the bigger angle, and it's opposite the bigger side, which happens to be the square root of 3. This one just happens to be 1, and this one's 2. So if you just memorize that triangle, you can now find the sine, cosine, tangent, cotangent, secant, cosecant of pi over 3, pi over 6, and technically 30 degrees and 60 degrees, but we're working more with the radians right now. The other triangle, I apologize for writing this one so small, but they're the same thing. They're both pi over 4, which I think you recognize is 45 degrees. This is called the 45, 45, 90 triangle, as you can see again. But this one has sides 1, 1, and obviously from the Pythagorean theorem, square root of 2. So memorizing both of these triangles allows us to figure out the sine, cosine, tangent, cotangent, secant, cosecant of pi over 3, pi over 6, pi over 4. And that's what we're going to do now. Now I'll show you how to actually figure out what those are. Of course, remember our sine is equal to opposite over hypotenuse, so we're going to use our mnemonic. Some old horse came a-hopping through our alley are, here's the alternative version, which more people know, I think. So, ka, toa, SOHCAHTOA. Okay, so sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So if I want, for instance, the sine of pi over 6, I just look at this triangle. I got to do pi over 6, so that's got that guy over there. And sine is equal to opposite over hypotenuse. The opposite is 1, the hypotenuse is 2. The hypotenuse is 2, so that's 1/2. Cosine of pi over 6 Cosine is adjacent over hypotenuse. So adjacent is root 3, hypotenuse is 2, so this is the square root of 3 over 2, which is about 0.866. And tangent, pi over 6. Tangent is opposite over adjacent, so opposite is 1, adjacent is square root of 3, so it'll be 1 over square root of 3. Now, we don't like radicals in our denominator, so we can normalize this by taking the square root of 3 and dividing it by the square root of 3 and multiplying that. That's just 1. That's why we're allowed to do that. So this becomes a square root of 3 over 3, because the square root of 3 times the square root of 3 is, in fact, 3. So now we've got sine, cosine, and tangent. If we wish to see cotangent of pi over 6, that, of course, is just 1 over tangent. And therefore, we get 1 over this would be the best way to deal with that. So this is the square root of 3. If we want the secant, pi over 6, that, of course, is 1 over cosine of pi over 6. Cosine of pi over 6 is root 3 over 2, so this must be 2 over root 3. But again, we're going to have to get rid of that radical in the denominator, so I multiply by square root of 3 over square root of 3. This becomes 2 square root 3 over 3. And then finally, if I want cosecant, pi over 6, that's 1 over sine of pi over 6. So sine of pi over 6, and I need to focus that a little better, especially since I'm using blue. The cosecant of pi over 6 is basically 1 over the sine of pi over 6. The sine of pi over 6 is 1 over 2, so this will just be 2. So now just from that triangle, I've gotten the sine, cosine, tangent, cotangent, secant, and cosecant of pi over 6. Now you can do the same thing with that triangle for pi over 3, and then you can come over here and do it for pi over 4 as well. So let me start. I'll just write these down. So I'm going to say sine of pi over 3, cosine pi over 3, tangent pi over 3, cotangent pi over 3, secant pi over 3, and then cosecant pi over 3. Now from this we can see sine of pi over 3, opposite over hypotenuse, so that's root 3 over 2. Cosine pi over 3 is adjacent over hypotenuse, that's 1/2. Tangent pi over 3 is root 3 over 1, so that's the square root of 3. Cotangent pi over 3 is, tangent was adjacent over hypotenuse, which was 1 over square root of 3, sorry. So that should be square root of 3 over 3. Okay, cotangent would be the inverse of that, so cotangent would be adjacent over hypotenuse instead of opposite over adjacent, adjacent over opposite instead of opposite over adjacent. So adjacent over opposite is 1 over square root of 3, and that would be, wait a second, tangent pi over 3 is opposite over adjacent. That was just square root of 3, which I got right the first time. So I did make a mistake in making a mistake about my making a mistake. Cotangent pi over 3 would be adjacent over opposite that. So that would be the square root of 3 over 3. Secant, of course, is 1 over cosine, so that would just be 2. And cosecant, of course, is 1 over sine, so that'd be root 2 over, 2 over square root of 3. But that becomes 2 times the square root of 3 over 3. So now we've gotten the 6 trig functions for pi over 3 as well. I was going a little fast and hence made a mistake here, but luckily we caught it in time. And now you can do the same thing, of course, with pi over 4. So then doing that, you can come back and look at this and say, oh, well, let's pretend this is the angle theta. Well, I know that angle's pi over 6. So if I want to find the coordinate of that, that's the x comma y coordinate of this, then all I have to do is imagine that right triangle and use trig functions to figure out, since the hypotenuse is 1, what is the adjacent side and what is the opposite side. So clearly the opposite side is going to be given by sine and the adjacent side is going to be given by cosine. And one by one, I can figure out the x and y coordinates of all that. The more difficult thing is when you deal with the zeros, the 90s, the 180s, the 270s, and then the next more difficult thing is dealing with these angles, because this angle, notice, you can't, I haven't shown you any triangles to get you the 90 plus 60, or excuse me, the 90 plus 30, which is 120 degrees. But here's the cool part. You can use the fact that this is just 30 degrees, and long as you keep your sign straight based on the quadrant you're in or based on where you're at on the XY plane, then you can still use a smaller angle and fix them all. That's what we'll do in the next lesson. I'm going to leave for you guys to, one, fill out this for sine of pi over 4, cosine of pi over 4, tangent pi over 4, cotangent pi over 4, secant pi over 4, and cosecant pi over 4. And then I want you to start thinking, once you've managed to figure that out, I want you to start thinking about what would these angles, how would you get x and y for this point, and how would you get x and y for this point, and how would you get x and y for this point, as well as how are you going to get x and y, or excuse me, how are you going to get the sine of 0 and the cosine of 0 and stuff like that. So that's about it. I hope this helps. Have a good day.